Thank you, Pinaki. As some of you might have realized, too loud, right? Okay. This is the first time I lecture on this material, so it's a real pleasure to do so. But also means that unavoidably I make a few mistakes here and there. You know, just I just noticed the T-shirt. Yes. So this is what's happening to my family while I'm here. As you can see, they miss me dearly, and so they lie on jammed systems, partially liquid, partially gel kind of material. Anyways, so yeah, so it's my first time teaching this. So at the end of yesterday's lecture, I asked for feedback from people how they thought it was going, and I got some very interesting and contradictory responses. The first one was that I went too slowly. This was, and the second one was that they'd like me to repeat part of the material because it went too fast. So, what? But repeat faster. So I'm going to take a vote, right? So, who thinks here that it went too slowly yesterday? Shri, I don't see your hand. What? Was this? Well, I know, but I would like to see it nonetheless. Okay, so to be disregarded, who would like me to repeat the part about the simulations because they thought it went too quickly? The final few slides? Okay, is this a critical mass? Yeah, okay, whoa, yeah, we do have a critical mass. Okay, now that the front rows have voted, you guys? I didn't see much hands, but okay. So that's what we're going to do. We're going to adjust. Well, we have plenty of time tomorrow anyway, so it's not the end. But before I do this, there's a few things, and there's also some smaller corrections that I need to make, and I want to do them now before I forget. The first one, so Jorge insisted that I would not use the terms paradigm shift to describe his work in front of him ever again. So it's crossed out from the slides, and he's not here today, unfortunately. That's Gestalt. Just for Jorge, actually. So that's one part. Something a bit more serious, and I should have said this. This is really a mishap. The program that Parisi and Zamponi and others performed is actually strongly inspired and initiated by the work of Kirkpatrick and Walnis from the late 1980s. And this was actually the idea of looking at the glass problem in high dimensions as a way to make sense of what's happening was first attempted in that paper in 1987. And actually the description to a large extent of the glass transition and of this configurational entropy was formulated by Kirkpatrick, Thermali, and Walnis a couple of years later, and it's been historically been named random first order transition theory, making reference to actually the Kautzmann transition, to which I think Ludo will get tomorrow, in particular, right, as part of the scenario. So they really remarkably intuited material that would then take the rest of other people, turns out more than 20 years to even start addressing and 30 years to roughly complete. Right, so a lot of credit needs to be given for this non-paradigm shift event. Okay. So I'm going to repeat a few things that I said about what I said about running high-dimensional simulations, and I've prepared a few pictures as well. So yeah, we'll leave those up, but just don't look at them for now. They're not really useful. Okay. So one thing that one typically keeps in mind when doing simulations, something that's really important, it's the notion of finite-size effects. Right? We're already dealing with finite dimensional effects, which are really complicated. So if we at least could control what's happening in terms of our system size, then that's a decent start, right? That's something we can remove out of our heads. But at the same time, so ideally, maybe ideally, actually I don't quite agree with this statement, but ideally we'd run a system that's so large that there's no finite size effects. That you don't so large actually that you don't even have to care about finite size effects. Maybe that's a better description. But that's really in other ways, a waste, right? You don't want to be running systems so large that you're wasting your computational cycles, right? Computational cycles warm up the climate. They cost money. They, you need to apply grant time or to get them. So you want to do the system as large as you need to, but no larger, ideally. So it's important, if you want to do this correctly, to think about what the finite size effects are typically in a system. And the most fundamental one, the one that you can't get away with, whatever you do, if you calculate any thermodynamic quantity, you'll get something that scales like 1 over the system size. There's a correction to the free energies, to the pressures, that will go like 1 over n. So depending on your tolerance to risk or to precision, sometimes 1 over n, maybe it's 1 part in 100, 1 part in 1,000, right? It's typically small enough for the amount of averaging you're willing to make. So that's the part that you will never get rid of. But if you can keep the other finite size effects smaller than 1 over n, then you're in good shape. And that's sort of the target. So this is inherent finite size effects you can't escape. So that'd be the first type. The second type, you would come from structural correlations. Right? And we've looked a bit at those yesterday, the complex structure, right? There's some structure that's non-trivial in 2 and 3D for 1, 2, 3 different solvation shells, depending on the density you're looking at, right? So you'd ideally like to have a system that's large enough that you reach the ideal gas limit, or the truly random distribution of system in that case. Now, as you increase dimension, I've argued and I've showed to you that those effects actually go down, right? If you reach 8 dimensions, for instance, essentially anything beyond the first solvation shell is indistinguishable from an ideal gas in terms of structure. So it's really, we're helped in going to higher dimensions in this respect. But we don't want to sin through the other direction either, right? There's sort of you could get ambitious and say, well, I have a box, and all I really need is 1 particle and a few particles around it to represent 8D. You don't want to do this, because if you start having, let's say, a box that's a bit smaller than 1 particle, than 2 particles wide, then you can run into situations when this particle here cannot pass the other. I mean, it can go around it, but it can't pass it this way. And actually what you have in this case is that, you only really have 2 body correlations, as you'd expect in high-dimensional limit, but you correlate with yourself through a sum of 2 body correlation. So as you go to higher dimensions, this is less and less of an issue, because the number of directions that are of size L, right? L would be n to the 1 over d, shrinks compared to the diagonals you have. You have many more diagonals that are longer than this size than it is. But so eventually you might be able to stop caring about it. But in 4D and 5D, there's still there's still 4, 5, 6 of those directions out of a total of different characteristic lengths. So you got to be careful. Essentially, if you're all the way down to 8D, you need to have at least a box size that's twice the particle diameter. Otherwise, you're including those spurious correlations sort of manually. And if you go beyond this, you might eventually be able to get rid of those. Right? And one thing to keep in mind, right, in this respect, that is going to be helpful, and something you can do, it's a small calculation that Francesco suggested yesterday. You can say, well, if I take 2 points at random in my box, right? How close by are they? Right? So you can do this. You say, well, I take my box and I can do each component. I can treat each component the same way, right? Because I'm just looking at xi squared minus xj squared, xi minus xj squared, and I have d components of those. Right? So I just need to calculate what's this average for one component multiplied by d, or square root of d at the end, because I want to be doing, this is really what I want to be looking at, right? Square root of d times this number is going to be the average distance between 2 points taken at random in my box. So I can do this calculation. It's 1 over L squared. They're flatly distributed throughout. There's two integrals, 1 over xi, 1 over xj, xi minus xj, square. And you can do, plug into Mathematica if you're lazy like I am. And this gives you, and you integrate from 1 to the box side, or from 0, sorry, to the box length in both directions. And what gives you is L squared over 6. So once you plug this number in, it gives you that this grows like square root of d, L over square root of 6. Right, so if you take 2 points at random, they grow further and further apart from one another, meaning that they are much more likely to be found along the diagonal or one of the diagonals than they are to be one of those directions. So if you get in a regime where d is large enough, you might be able to forget about those, to forget this condition that you might encounter. Okay, so that's the structural correlation side. This is something you need to take into account. The third one I've listed, we're looking at critical phenomena. Right? We're going to be, and we're talking today about dynamical criticality in particular. Yeah. Well, both, right? You want to be, what's the minimal size and how large do you want it to be? Right? Your computations don't scale nicely with the size of your system and dimension. So you want to try to minimize this. I mean, the size of the number of particles you have to simulate will grow like L to the d. So if you make a very small change and d is 10, you can speed up things quite a bit. Okay. Today we'll talk about dynamical criticality, and we'll have more to say about this, but one thing to keep in mind when you're looking at a critical phenomenon is that you have a diverging length that accompanies it. So you want that diverging length to be, well, in the regime that you're looking at, you want that diverging length to be smaller than the size of your system, right? Obviously, this is impossible in general. You can't get, if it truly diverges, at some point, it will become larger than the size of the system. But, so you should be looking at a regime where that critical length is not too large. One thing that does help you as you go to higher dimensions is that the critical regime becomes narrower. Right? So you have to be closer and closer to the critical point to have this length grow significantly. So it's something to keep in mind, and we'll talk about what this length is just in a few minutes, but we're a bit helped by the fact that we're going to higher dimension, by the fact that we can approach phi d, or the critical dynamical transition, more than we could in a lower dimension for the same correlation length. Okay, something Ludo will talk about tomorrow, he promised, is point to set correlations, which are, structural in nature, but of different type than what you would see in, say, a pair correlation or three-body correlations. And he'll detail most those in detail as well. And these actually do also diverge. So it's another length scale. So there's a length scale associated with dynamical criticality, one associated with those point-to-set correlations, but they diverge at a point called phi k, which is the Kaufman transition, which again, Ludo will talk about tomorrow in that context. Now, there's two things that help us, right? First, the fact that it's a critical point and that we're going to higher dimension means that you need to be closer and closer to that critical point to see significant increase in that length. So that's aspect number one, the same as in point 3. The second one is that phi k actually gets to be further. Right? This is something Francesco did not mention, but what we're going to have is that phi d scales roughly like 4.8, well, let's say d 2 to the minus d as you increase the dimension of space, while phi k is going to grow like d log d 2 to the minus d. So not only is the critical regime gets narrower, but the critical point is going to be further and further away from what we can actually approach as you increase dimension. Right? So as long as we stay in the dynamical regime, the critical dynamical regime, we won't have to worry about this particular length scale interfering with our measurements as well. And then the last one, the one I mentioned in closing, was hydrodynamic interactions. So if we're in a system where we have a particle and there's a conservation of momentum, so if this particle moves this way, there will be a backflow from the other particle so as to compensate for this displacement. Right? And the way this backflow decays is like 1 over r to the d minus 2, which means in 3D it's pretty long range. And the finite size effect that this follows, in particular, if you're looking at the diffusivity, to use Francesco's notation, some beautiful D, okay? It's going to be there's some bare diffusivity. I don't know how he does this. It's very pretty when he does it. Times a minus hydrodynamic length, or the size of the system, to the d minus 2. Right, so if you look at the diffusivity in a finite size system, there's always a correction that comes from the fact that there's, in a sense, the movement of the particle here is coupled with that of its image in a different box. You do something that's like an Ewald summation. So it's a slow decaying interaction, just like Coulombic interactions are slowly decaying in a charged system. And the net correction is 1 over L in 3D, which is pretty huge, actually. It's easily measurable. But as you go to higher and higher dimensions, d minus 2 starts to look a lot more like d, and therefore this correction becomes comparable to 1 over n. So already above 5 dimensions, it's really hard to measure this effect, right, in any reasonable system sizes. Okay, so that's what guides us into making measurements and into simulating higher dimensional systems. One of the questions that was asked to me after the fact, after class, which I thought was a very interesting one, I should have probably brought it up, said, well, you showed us results for G of R in 8D, right? I had this plot and had some sort of peak and essentially no structure beyond it. And you went to somewhere like 6 particle diameters, right? So this is R over sigma particle diameter. And you told us that there was only 2,000 particles in the system, right? How can you do this, right? Because if you, the general recipe, if you open Frankel and Smith and you look at what's the recipe for calculating G of R, it says very clearly, right? You look at your neighbors within a full complete spherical shell, and that means that you can't go any further than box side L over 2 for G of R, and that's true everywhere. So now your box side is 2, roughly 2, maybe 2 and some fractions. How can you report things that are going up to 6? So you know, but anyway, does anyone? I've actually sort of mentioned what the answer could be already today. So why can I go all the way to 6? I told Ludo also yesterday. He also asked. Actually, Ludo's questions was more cynical. Isn't there any tricks? You know. No one. Where do I get particles? How can I get data about something that's larger than the box side? Over 2. It's periodic boundary conditions, but then I would be getting, if I were to do this, I'd just be getting information about myself, right? So I'd find some structure at a certain distance because I would be there. So that, yes, I'm using periodic boundary conditions, but that, it really doesn't help you here. This would give me more structure than there is in liquid, really. So when this algorithm for computing G of R looks at the inscribed sphere within the box. Right? And one thing I mentioned also yesterday is that the inscribed sphere becomes a smaller and smaller fraction of the volume of the system. Because in those diagonals here, in those corners, there's really a lot of space. There's a lot of particles that are completely uncorrelated, that are not your periodic image, right, that are present. And I can go and measure their contribution. Actually, those parts of the shells are so big, I really have a lot of data that I can extract. And this is how I can go all the way to 6 sigma in 8D. Right? The longest diagonal is something like the square root of D. So if square root of D, square root of 8 is roughly 3 times a box height of about 2. That's how I got all the way to 6. Right? So that's this is data that in 2D and in 3D you typically throw away because you say, well, it's not worth my effort. But if you're just willing to compute what's the volume of a partial spherical shell, which you can do analytically, but it's kind of painful. You can do by Monte Carlo simulation, just throwing dots at random. It's really easy and efficient. So that's one thing that you can do. Okay. Now, I mentioned a bit computational efficiency yesterday. That's the one thing I did mention, and I was mentioning how you don't want to be using cell lists. You want to be using Verlet lists alone, right, when you go to higher dimensions, because you don't have enough boxes to make cell lists useful. And at the same time, this inscribed volume is very small, so it's really quite an acceleration on your dynamics, even though ultimately you'll get an algorithm that scales like the number of particles square. Right? You just can diminish the prefactor in front of that n square scaling, because you need at some point to look at all pairs of distances. So that you can't escape, but that's you can try to make this as less painful as possible. And this is actually a recommendation from and another question that came up actually while we were having a high tea was, well, couldn't you do better than a cube? Right. One of the problems with the cube as you go to higher dimensions, and this is sort of a 4-dimensional representation of a hypercube, but the higher in dimension you go, the more the cube looks like this. Right? You get those really deep angles, like edges that go really far, and then you have some constraints that come from those tiny directions. Right? You don't really have one length scale that you're probing, because there's one length scale that's L, and then there's all those other longer length scales that you have access. If you have something that's more spherical, you can do better. Right? And in 2D, the optimal shape you could use for a box is actually, it's not a cube, it would be a hexagon. Right? Essentially, it's a Wigner-Seitz cell of the densest packing in any given dimension, which for a triangular lattice is a hexagon. It's optimal in the sense that you get. It's optimal in the sense that the inscribed sphere on outer sphere is the smallest radius possible. So you minimize the mismatch between the short and the small directions. So that's the way it's optimal. In 3D, it would be the FCC Wigner-Seitz cell, which is some rhombic dodecahedron. If you were to do this in 4D, the densest packing is D4, as I argued yesterday. The Wigner-Seitz cell is called a 24 cell. It's a very, very dense polytope. And if you do this in 5D, it'd be a different one. And actually, it's true, we could do better than just a simple hypercube. The cost is that then you need to code a different set of periodic boundary conditions for each dimension, right? Which is not a trivial task. And actually, the crystal geometries themselves, in, for instance, 6 and 7D, are pretty involved. So it's a lot of work to do so. But if you really, really care, you could probably shrink a bit that prefactor again in your computational costs, because you can, not the prefactor, but you could shrink and emit a factor of tens of %, which can be significant, but not factors of 10. So depending on where you want to invest your efforts, you may want to be considering this option or not. That's all I wanted to say about simulations. Is that enough? Do you want to know more? If you have other questions, by the way, few people on the planet have coded higher dimensional molecular dynamics code, and some would argue for very good reasons. But you know, if you ever face this conundrum, I'd be more than happy to help you out, because 13 actually. We published 12, but we did 13. Well, so Francesco told us how we should be thinking about scaling up our potentials with dimension, for instance, right? To make sure that this long-range contribution does not diverge when you integrate, so to have finite energies. So the range of attraction shrinks. Yep. So what you're trying to minimize, in a sense, is the mismatch between your long and your small directions. So ideally, the optimal one is to have a circle, right? But you try to implement circle, because the densest packing in 2D is a triangular lattice. The Wigner-sized cell of a triangular lattice is a hexagon. That is, so that's the optimal you can do. And if you want to read more about this argument, it's actually a paper called The Dark Side of Simulations by Don Frankel a few years ago. But yeah, and actually in Allen and McDonald's 1987 book, also they discuss, I think it's the most recent pedagogical discussion of this effect, if you're curious. Well, it depends on no, edges on their own is not sufficient. There's some, it's how it gets inscribed in a sphere. Okay. I think this is all I wanted to say for this. Let me just check what's my next slide. Oh yes, yeah, there's something I forgot also. There's another question that was brought up, a small correction. So as Francesco showed, you define this little p called beta big P over rho, right? This is sort of the compressibility. And this, if you expand, would be 1 plus B2 times rho in plus high order terms, but in infinite dimensions, only these two terms survive. Right? And the question was, well, are you sure? Are you really collapsing those results efficiently? Or is this distance an artifact of the fact that I'm not taking into account? And I answered wrongly, but the correction is small. So this is what I wanted to show. B2 so B2 rho you can rewrite as 2 to the d phi over 2. Okay, and then what you do, so you're doing 1 over, well, d over p, or little p. This becomes 1 over d plus 2 to the d phi over d, and there's a factor of 2 somewhere, which I think 2 here, right? So when I'm plotting this, there's when 1 over d is small, this does tend to be 2 over x as a curve, right? But in small d, there's 1/3 or 1. So there's a small 1 over d correction that's not there, but it's not sufficient to make this collapse. Okay, so it's close to being what I said. And if you want to do this really cleanly, you just subtract 1 before taking the inverse, and that would have a slightly nicer scaling. Yes. Okay, so that was another point. And then the next one brings us back to the program for today. Okay, so now I can review what we did yesterday and look at what we're going to be doing today, having said that. So the first thing we did yesterday was to completely eliminate the worries about crystal nucleation when you go to higher dimension. Right? There used to be some other words here, and technically, it's not that it's not happening. There could be crystal nucleation, but it's such a rare event that you really have to be bad lucky for it to interfere in your simulation. Then we looked at the notion of the complexity of the structure and how the structure does become simpler as you approach infinite dimension, but but it persists, right? It's an annoyance. It is simpler, but not so simple that you could just forget about it. So it'll remain part of our concerns. And what we're going to be looking at today are things having to do with criticality of the dynamical transition. And one thing that's great about criticality in general is that it gets rid of, by the fact that you have a diverging length scale and diverging time scale, it sort of washes away all sorts of small scale structures. Right? The Ising universality class, for instance, the system doesn't care whether it's on a cubic lattice or FCC lattice or something similar. You always get the same critical exponent if your dimension is fixed. So you could think that by looking at something that's critical, you might be able to forget about the fact that you're having a complex structure system. And that's what we're going to be looking at first today, and then we'll look at other problems with criticality in 3D. Okay, but before we do this, let's look at one result that Francesco showed in his lectures. You mentioned the Stokes-Einstein relation in higher dimensions, and the result he was quoting, and we're going to be looking at dynamical criticality that happens when diffusivity gets slow, when this product here gets, when you have high packing fractions, when you get to be at this end. But let's first look at what happens in the liquid, right? Before this memory contribution has a great significant impact. Right? So Francesco's general result was if you were multiply beta times the diffusivity, script D, eta S, what you obtained was 2 to the D times var phi. So something linear in packing fractions. And actually he obtained this in the entire liquid regime all the way to phi D. All the way to when the dynamics truly arrests and the viscosity diverges. And one thing that's actually very nice about this result is that it's not a property of the glass formation itself. This is really a property of high-dimensional liquid. It turns out if you remove all notion of memory, right, if you make this kernel become trivial, you recover the same scaling. Right? Then this is what you're seeing here. So you're looking at beta D times eta S, and as you increase dimension, you can see clearly this linear regime in 2 to the D phi emerging. So this goes all the way to 8 dimensions. So if you're looking in 3D, this is the regime where people have called some Stokes-Einstein effect, and it does look flat over this tiny density regime. But you can sort of guess that the reason why it looks flat is because it doesn't have time to turn and keep increasing before it starts reaching the dynamical transition. That's one thing. Then, but if you go to 4D, you start seeing something a bit more straight, and 5D also. And in 8D, you have something that's almost convincingly straight in this way. A bit off in the slope, maybe within the error bars. But yes, Sri. Please take the mic.
No, I mean, as you go to higher dimensions, you have better agreement with the high dimension or D tending to infinity limit. But that doesn't necessarily, in a very straightforward way, tell you anything about what to expect in 3D, right? So, for the sake of argument, it may well be that there is a well-defined Stokes-Einstein regime for three-dimensional glass formers.
You could, but then you would find that actually the scaling, the constant is wrong, right? Which is what it is when you look at self-diffusion in 3D. It's off. I mean, we can get into this. You can go into a lot of details about this, but it's never Stokes-Einstein in 3D. For self-diffusion, it just happens to be relatively flat. You have some divergence at small packing fractions that comes from this kinetic theory description, okay? And then you have something that looks flat for a while. And what's interesting, and what's been called a Stokes-Einstein relation breakdown, actually, in glass formers, you see that there's this really sharp shooting up as you approach phi d, which does not exist in the infinite dimensional solution, and which does become smaller and smaller as the shooting up as you increase the dimension of space. right? And maybe we'll talk a bit about this breakdown. I was not planning to, but that's clearly a sign that something is different. That's a clear sign that it's something different from the infinite dimensional solution. This Stokes-Einstein breakdown does not exist, right? You have deviations from the naive Stokes-Einstein, but and that's predicted by the theory, but not this shooting up at high packing fractions. And you can see how significant it is in 3D. Clearly, this is not something that can be neglected in 3D. You might be able to neglect it in 8D, but not in 3D. Right? So that's a hint that there's something really different between this scaling and what we observe. Okay. Let's talk about criticality. So Francesco mentioned it, a bit of it in passing when he was lecturing. I think this is where my note is. And he focused on one quantity in particular, and then Sri mentioned more in his lectures on Monday. Right, but the basic quantity that you're expecting to diverge says that the relaxation time, or the inverse would go to 0, and in this line of argument, you expect tau alpha to scale roughly like d, or if there's a difference between the two, it would be sort of the linear level, maybe a factor of 10, but not factors of millions. And this would scale like some critical dynamical packing fraction versus the packing fraction to some power gamma. Right? That's the theoretically predicted critical divergence of the relaxation time upon approaching the dynamical transition. Theoretically, because phi d actually has a lot of structure, right? Because liquids have a lot of structure, theoretical predictions for phi d are not very good. Right? You can't really rely on them to do your fits. It's a bit the same way that the mean field Ising model doesn't help you make a critical fit for the critical temperature by giving you the value of the critical temperature, right? You have somehow to figure this one out differently, and then you can do your fit. So it's used as a fitting parameter because we can't find something precise enough to be able to fit. In the Ising universality class, one thing that helps you is that this critical exponent, or the corresponding critical exponent, say for magnetization, is universal. Right? It doesn't depend whether you're looking at one lattice form or another, right? It all gets washed away. But one of the problems, or one of the difficulties when you're trying to do this analysis for the divergence of the critical time is that gamma itself is not a universal quantity. So phi d here depends on structure, and therefore on dimension, and therefore on the interaction potential, and so does gamma. Right? So you have two parameters for which actually theoretically you can make some predictions for those two. They're just not precise enough to be able to use them. Right? The uncertainty on gamma that you get from the theoretical predictions are of the order of 10 to 20%. Right? And the uncertainty on phi d are also 10 to 20%. So you can check that what you use as parameters makes sense. You're not free to fit broadly without constraint, but it's still not enough to check whether you have something that's critical. So what you have on the right here is some attempts at making critical fits in dimensions 3 to 8. Right? And one thing that you notice, so this is 3, and then it increases all the way to 8. So there's something that looks like a critical regime for maybe a decade and a half, maybe 2 decades if you want to be generous. And then if you get closer and closer to the putative dynamical critical point, you start to see deviations. And you see the same in 4D to some degree. In 5D, those deviations, I know they're still noticeable. In 6D, you have to go closer and closer to 5D to see them. In 7D, if they do exist, they're beyond the dynamical range of what we could reach when we published this paper. Right? And in 8D, you get a really nice, essentially 3 decades solid dynamical regime. Right? So clearly, fitting with phi d is not a ludicrous idea, but it's less of a ludicrous idea the higher dimension you go. Right? And we'll try to understand why that is. Right? If this were a real critical point in finite dimension, you wouldn't have those issues. You'd be able to fit as much as you want. It's not that those systems are too small. This is not a finite-size truncation. This is a real truncation that comes from the physics of the system, not the fact that we're using a simulation box of a finite size. Right? If you're doing Ising model simulations, you would see deviations like this, but because you are hitting the walls of your system. But this is not what's happening here. Right? The correlation lengths are still small compared to system size in 3D, and we're seeing visible. Sorry? Okay. So one thing that I forgot to mention when I did this, so D suffers a lot from hydrodynamic correlations. Tau alpha, not so much. Actually, there's less finite size effect, and because the viscosity itself, where tau alpha is a better proxy of, is essentially insensitive to system size beyond a certain threshold. So you have to be careful in low dimensions if you're looking at D, but not. These are tau alpha. And this is D, and it's 3. And that said, on a logarithmic scale, you wouldn't notice a difference. Okay, they're important. They wouldn't affect the critical scaling on this type. Those systems are actually not worse off because of that. But very good question, actually. Yes, this is D. Thanks. And what you fit here on the left are the gamma. Sorry, what's here on the left are the reported gammas. So those exponents that we fitted to those lines that look broadly reasonable. And there's an attempt at making honest error bars on the uncertainty from the fitness. In 3D, there's really a lot of uncertainty because the critical range that you're trying to fit is small, and you have a lot of degrees of freedom by just having those two parameters to fit. As you go to higher dimensions, the error seems to be shrinking. And one reference point that we do have is the infinite dimensional solution, where this transition really should be critical and for which we can calculate the gamma analytically without because the structure is trivial and because the interaction potential we control, right? And that's the dashed line here, the red dashed line. So qualitatively, we do seem to be getting closer and closer to this limits monotonically. So it's physically consistent with the expectation, right? But it remains a part of an art form. There's some discomfort that goes with this. Okay, so that's the first sort of fitting. And I mentioned that there's a critical length that's associated with this diverging time. And the critical length you can see by looking at what's called a 4-point correlation function that Sri mentioned on Monday. It's commonly called G4 of R and T, 4 for 4-point correlation. And it would be looking at a 2-time and 2 points correlation. So you'd be looking at, say, the correlation at position R, position T. So this could be, for instance, Fs, the local Fs that was looking at, so 0 in T, right, minus the connected term square. And you would expect this quantity, right, at a given T to scale to have some some correlation length, sorry, that describes its long distance decay, is xi, that depends on the time at which you're looking at, right? And xi itself, at least on tau beta, on the beta relaxation time, would itself diverge as phi d minus phi to some power minus, right? So this is the correlation. One other quantity that Sri introduced is the integral, essentially, of this correlation function. It would be chi4 as function of time. It's the integral over all space of G4 of R and T. This is the end of where I'm allowed to write, right? So if you have something that decays very slowly, it has a fat tail. If you make its integral over all space, you'd get chi4 to diverge when you get a divergence of this correlation length. Right? That's the That's the idea. So you'd expect, based on this sort of critical reasoning, that you would see, if you were to plot chi4 as function of time, as you approach a critical point, where you go up, and then would get sharper and sharper. And this peak here is the point, as Sri argued, is the point of maximal or dynamical heterogeneity, or maximal dynamical heterogeneity, where you see more and more stronger and stronger growth of those heterogeneity as you approach the critical point. Yeah, I've skipped over a couple of things. I'll come back to this. Right, so this is what a function G4 could look like. Right, you see that there's an exponential decay as a function of r. These are calculated tau alpha. And this tail becomes fatter and fatter as you approach the putative dynamical critical point. And this is what the function could look like. You could integrate it and get chi4 functions like this. Right, what you're seeing here on top is what dynamical heterogeneity could look like. Right? But if you take it literally, what this dynamical heterogeneity means that you have different regions of the system that are relaxing at different rate, right, over some time scale. Now, one thing that one needs to be very careful about when thinking about dynamical heterogeneity is that if you have parts of your systems that are structurally different, they will also relax differently. Right? If you have a crystal with defects, the part that is defective will relax differently than the parts of the crystal that are not defective. Right? It's a complete sensical description. So if you have a system, like we argued yesterday, where there are some structure that are present, right? We were looking at potential realizations of polygons that you can find in the liquid, as Paddy Royale and others have developed. Well, different local environment can result in slightly different relaxation times. Right? But these are not the dynamical heterogeneity that are associated with the critical point. These are structural heterogeneity which impact the dynamics. Right? The dynamical heterogeneity that will be the relevant ones are the ones that do not depend on the structure. Right? This is what the theory predicts, because the theory doesn't know anything about the structure, and if you're seeing a divergence without any structural sign, that's the dynamical heterogeneity you're looking for. Now you can imagine this makes it quite challenging if you're looking at three-dimensional systems and trying to look at whether looking at three dimensionals and try to determine whether the system behaves critically or not. Not only that the critical regime itself is short, but on top of this, you have to disentangle what's the contribution to the heterogeneity that comes from heterogeneity in structure to those that come from the heterogeneity in the dynamics purely so. Right? So how do you do this? Actually, this is not a well-resolved problem. It's not a solution that everyone agrees on. It's a bit in the eye of who makes the measurements and who makes the approximations. One thing that going to higher dimensions allows you to is, first, it increases the dynamical regime over which you can look at this and presumably be critical. And second, the role of structure gets diminished. So you can be maybe more confident in what would be happening. Yep. No, this is 3D data. And this is actually, you're bringing up exactly the point I wanted to make. No one's checked. Yes. Surprising that we asked our postdoc to do it, right? So no one's looked at this yet. Right? That's what we expect. It's really computationally demanding. It's computationally demanding quantity to average in low dimensions. It only gets worse in terms of averaging in higher dimensions because your systems are a bit smaller. But that's, it's sort of a frontier in high-dimensional simulations, something that we're trying to do now. And so looking at this particular defect, if you go above the dynamical transition, there's also predictions as to what should happen to chi4, right? Above the dynamical transition, the structural relaxations don't disappear, but you may have some heterogeneity in how certain cages are with respect to others, right? And actually the prediction so in that case, if you look at chi4, it would be measuring differences in caging throughout the system, right? So if all the cages were the same, you get a small chi4. If they're very different, you would get a large chi4. So you'd expect that the long time behavior of chi4 from above would grow up. So this would be chi4 of t goes to infinity for phi above phi d. This is phi d. You'd expect this to grow quickly. And Francesco also mentioned another prediction that you would get for above phi d is the cage diameter itself, the mean cage. So chi4 is sort of the variance in the cage. The mean cage would have a square root singularity at phi d. So this would be the average of what you call the average of d, right, in this notation. So this does not diverge, it goes to a constant, but it approaches it at a square root. And you should be able to see this more and more. At least this is the mean field prediction, the square root. The exponent in low dimensions could be different, right? But that's the sort of questions that one could be able to explore if we were to look beyond phi d, if we were able to equilibrate this way. I think in this respect, Ludo's talk tomorrow is going to be very instructive, right? Maybe. Okay. I think it's going to be very instructive. Okay, now going back to the slides I skipped. So I said there's a lot of uncertainty in phi d. When you try to extract it, it's sort of a difficult sport, but it turned out to be a very useful thing nonetheless to look at it as a function of dimension 7 or 8 years ago. Right? Because 7 or 8 years ago, there was this controversy that appeared in literature, and as we were discussing earlier today over brunch, about how one should expect the high-dimensional scaling of phi d to go. And that's at a time where the theoretical basis for Francesco calculation were a lot weaker than they are today. So there's a prediction for how the dynamical transition goes, 4d times 2 to the minus d, as I was saying before. And at the same time, or about the same time, there's two independent computations of what the mode coupling theory that Sri introduced on Monday, how the predictions, the transitions it was making would scale with dimension. It would scale like d square 2 to the minus d. Right? So as you go to higher dimension, this would be infinitely denser than this one. Right? And this was at a time, again, of theoretical uncertainty, where the world of glasses was still in crisis. This led Jean-Philippe Bouchot to write sort of op-ed for condensed matter physics. It says, the mode coupling theory of superliquids, does it wear any clothes? Making a reference to the Danish king who would walk naked through the streets with the finest clothes he thought on his mind. So this is the reference I make. So we couldn't, directly access this numerically, but we could look at the low-dimensional scaling. Right? By low-dimensional scaling, I mean something between dimension 3 and 13. And we can look at the predictions of the two theories as a function of a dimension. So the red one is the mode coupling theory, which we know does a remarkably good job at predicting the dynamical transition in 3D. And we had found in the meantime that it does an even better job in 4D. But if you start stepping back a bit and looking at how it goes with dimension, it quickly just shoots for the sky compared to what you see numerically, the blue dots. While the replica theory, which obviously has issues with how it introduces notions of structure and how and finite dimensional corrections that may be in, it was still sufficiently precise to make a convincing case that it was a better description of what's going on as increased dimension than the mode coupling theory. And so this gave some impetus for pursuing research in this direction, actually inspired Jorge to suggest how one could make this, or the description of the replica calculation more formal so that there would be fewer assumptions that went into it. And their series of paper, followed after this. So it was one of the important tests of this description. Another thing I wanted to mention as we go along, and we'll go back to it, it's something that, and maybe one last thing about MCT. So mode coupling theory is still a really useful theory of liquids, but it has some fatal flaws. Right? Sri mentioned this one in passing. He also mentioned the fact that it predicts a Van Hove function becomes negative if you go to high enough dimension. So there's something wrong with it. one hypothesis is that somehow there's two terms that happen to cancel one another in low dimensions. This is what makes it, luckily find the right, or something close to the right solution in low D. That could be what's going on. Or there could be some term that's just small in low dimensions that grows larger as you go to higher dimension, and this is, because it doesn't include it, it misses completely what's going on. Actually, it's not clear to this day what's the problem with the mode coupling theory of Goetze and coworkers, right? There's no way yet to reconcile the two. It's an open theoretical problem. It's been an open theoretical problem for 8 years. And there's some ideas. People have tried a number of things that they thought could solve the problem, and none of them have worked at resolving it. So the number of possible ideas that is small now. Open challenge. We have a joint postdoc call with David Reichman. I'll be interested in tackling some of the problems involved in there. So if you're interested, please talk to me or to David. It would be based in New York, so it's a nice gig. Okay, so that's one thing I wanted to mention about what we can do with Phi-D, despite the uncertainty and the weaknesses. Another thing I wanted to mention in passing is what's called the onset, the dynamical onset, which has not really been mentioned much thus far. But if you're looking at the mean square displacement, right, we've described how if you're in a very sluggish regime, there'd be some caging, and then there'd be some diffusive behavior at a long time, and there'd be some ballistic behavior at short time. And if you go further and further away from putative Phi-D, right, you'd see this go away slowly up until the point where you can't see any inflection anymore, where there's nothing that suggests that the system is sluggish in any way. Right? It just goes ballistically for a while, and then it bends a bit to get into diffusive regime. Right? And people have given a name to the start of this sluggish dynamics. It's called the dynamical onset. It's not a transition per se, right? It has no criticality in nature. It's just some place where things start to change from one type or another. There's been efforts to try to relate this to the potential energy landscape, right? Maybe there's some connection with what's happening in the inherent structures you're sampling, but it doesn't really matter. In any case, there's no theoretical prediction for what this should be. Actually, there could be, because Francesco has solved the dynamics exactly. He just can't solve the equations, right? So this is not something that you would see as a singularity. You would see this as, if you were to solve completely the equation, see where this onset is. So we can measure it as functional dimension, right? And it looks to be something that's roughly constant in 2 to the d phi over d, like within error bars. It's something like 1.2 times this number. And it has this quantity. But is this correspond? So this suggests that it is something like a mean field scaling, because it has the same feel as a mean field scaling. It also makes sense that this quantity would be less dependent on structure, because it's happening at a lower density in the liquid. So the details of the structure at about 45% packing fractions are much less significant than they are at 58. So, yep. Yeah. Yes, the answer. Yeah. It's not a systematic. It does converge to the right limit as you go to higher dimensions and quality. Yeah. Yeah, it's well enough. And actually, it doesn't really matter which closure you choose. Qualitatively, the results are similar, but you need to choose one. Okay. Anyway, so that's sort of a numerical predictions that's begging for theoretical corroboration or validation. That's still not happened. And I know Francesco has been looking to hire someone to do this particular work as well. Not this particular quantity, but more generally solve the equations of the dynamics. So if you're interested in this particular aspect of the dynamics, go talk to him. You can choose between Paris or New York for whatever you want to be working on. Okay. I think that's all I wanted to say about the dynamics. Let's just make sure that I'm not... about the criticality of dynamics. Because what we're going to be looking at next is all the ways in which this disappears. Yeah. Also, one thing, there's sort of, I mean, this is a mean field description of the dynamics that Francesco presented. So there's one very obvious way in which things can go wrong in any mean field descriptions, that you can go below the higher critical dimension, at which point things remain qualitatively the same, but with different scaling exponents. Yep. Which correlation function is function of time? No. I mean, gamma changes, so the stretching exponent does change. Right? The AB exponents change, but that's all controlled. We didn't try to do an extensive fit of the AB exponents to this, and for the reasons I'm going to be discussing, right? This criticality is really a transient in any finite dimension, right? So, how much faith you should put in any of those specific quantities if you don't master simple things. One thing that I do wanted to, I did say that this exponent here does depend on dimension and interactions, and it's a very fragile exponent in that sense. This exponent here in mean field is 1/4. It's the same. And here, this singularity is a square root in mean field, and that's for all dimensions and for all systems. So these are quantities that are robust within the mean field dynamics description. And if you're looking at finite dimensions, you have to worry whether the dimension is above or below the upper critical dimension, right? To figure out whether these are the good scaling exponents, right? And the upper critical dimension for this particular type of criticality is 8, right? So this is the Franz-Parisi potential. Or some versions of Franz-Parisi potential that sorry, it's my, yeah, that's but this is not delta. It should be minus delta. Oh no, 1/delta. Oh, I see. So it's flipped around. Okay, thank you. I stole it from his. So yeah, I have a feedback for your book now. So you should look about it. Okay, let me redraw it. It's not going to be. I thought I was going to be saving myself some effort, and then I just realized. If you look at this function of delta, right? This is the function that Francesco was drawing this morning. Right, the criticality corresponds to this becoming very flat. Right, this when phi is equal to phi d is when you have this spinodal in the order parameter. We argue that a spinodal in the first class is an upper critical dimension of 6 for an Ising model. If you have a system with this order, it's sort of a lore that you can increase the critical dimension by 2. In this case, it's also true. Actually, if you do the exact calculation, as Francesco and Pier Francesco and Silvio Franz and others have done in a PNAS in 2014, I think, and they look at the Ginzburg criterion and do find that the upper critical dimension is 8. Right? So even these exponents that are more robust, like the nu, like the square root singularity, in below 8 dimensions could be different, right? Could have different values, and one has to be careful when trying to fit to those. Right? So that's one way in which this criticality is to be taken with a grain of salt, at least, so below 8. There's a bigger problem. Right? Just like in an Ising model in a field, when you approach a spinodal, there's other processes that could be interfering. Right? So, someone responded to this question. I can't remember who it was yesterday. And what's the? Did he? Yeah. So what happens when you approach a spinodal annealing model that prevents you from looking at the criticality of the spinodal as you approach it? Can you say it louder? Like your advisor couldn't hear. You use a mic? Okay. Or you can speak. Nucleation. Thank you. Right? So if you are in this metastable minimum here, in infinite dimension, you can stay there forever. Right? Because this barrier here is infinite, because you can't form an interface. But if you're in finite dimension, you can have a nucleation process. And actually, we can write down a theory for what the free energy barrier should be as function of the radius of the spherical nucleus, right, or spherical-like nucleus that would be happening in this system, right, based on what Francesco and Ludo have said in the last couple of days as to what this curve is. Right, this is V of delta, which is in the same family as V of Q, with a few minor things. Right, so you know that there's a gain that you have from nucleating, right? If you leave this metastable glassy minimum, okay, what's the drive? What's the drive to leave this minimum? Did you hear it somewhere? Okay, oh, yep. Gaining entropy. Gaining, in particular, what kind of entropy? Configurational entropy, right? You have more configurations available if you can leave this. So you have a gain in configurational entropy. So I could write S-conf or the equilibrium complexity, depending on which one you want to prefer, right? Times which versions you prefer. So this is more finite dimensional quantity. This is sort of more mean field quantity, but in the high dimensional limit, these two should coincide. Right, so that's your drive. What's the cost? What's the cost in general? I mean, you're trying to form a nucleus of something. There's surface tension, right? Or some interface free energy. In the literature, they call it upsilon. It's an interesting choice. And it's not clear that your sphere is compact, right? It's not clear that the surface is smooth. So exactly how this scales depends on how you think what should be the precise shape of that nucleus. If it were a perfect sphere, this would be d minus 1. But if it has some sort of fluctuations around it, it can be an exponent different than d minus 1. And actually, in general, the proposed bounds for theta, it goes from d over 2 to d minus 1. This is a bound. This is not really a bound. It's more a heuristic argument. But that's, and the people, actually should say, who proposed this form, right? This is part of the original RFOT description. Adding on top of the model they intuited for how things happen in infinite dimension, they added a nucleation theory on top of this. Right, so you know that the criticality cannot exist in any finite dimensions because you can always nucleate out of it. Right, you can get some correlation time that gets to be long, but at some time there's there's some free energy barrier that you go over, and G is a function of R. The precise functional form, you're not quite sure, but it looks something like this. And if there's a time for this nucleation. If this time for the nucleation becomes comparable to your relaxation time, you will just do this instead of waiting for the dynamical relaxation that's diverging. Right? So it's always truncated in any finite dimension. You will never see a real divergence of tau alpha at the dynamical transition because this comes in and cuts it off. Now, as you increase dimension, this is a rare event. The interfacial free energy right? This will result in some barrier height, and just like the same argument we had for the nucleation of the crystal, the cost of forming the interface doesn't go to zero as you increase dimensions, so the fact that it's raised to an ever larger power will make this less and less likely. Right? So you can push it further away. So you can increase the window over which you can see the critical dynamical regime by going to higher dimensions, because you're sort of suppressing this process heavily. And that's one thing that would allow you to a nucleation-free system.
The relaxation time will never diverge, but this form will allow for it to diverge.
So the relaxation time will never diverge at the dynamical transition. At the dynamical transition. Because this process will come and chop it off. Right? So the mean field prediction for dynamical transition have issues with the upper critical dimension as to what the precise exponent should be. And on top of this, you will never get a long enough dynamical regime that you can convince everyone, because it will always be truncated at some point. And actually in 3D, we've seen it gets truncated about a decade and a half into its growth. Right? So in a sense, you almost need to believe that it's there to find it. If you go to higher dimensions, you don't need to believe that it's there to find it. It sort of jumps at you. But in 3D, it's a part act of faith, part observation. Okay, so I spent a lot of time talking about, let me just check what's my next slide. I think I've said what I wanted to say. Okay, in summary, right? We have complex activated processes that get increasingly suppressed as you increase dimension, which reveals a growing power law scaling, right? The quantitative tests of that criticality are not yet convincing, because the critical exponents are not predicted with sufficient precision that we could do convincing fits. Right? It's globally roughly consistent, but if we knew gamma, if we had a theoretical predictions for gamma that was within 1% or 0.1% of the true value, then we could really go and put our data on top of it and fit it and see that it works or not. But because we have such large error bars on the predicted quantities, because of the role of structure, of dimension, of the interaction potential in their calculation, that without going to high dimensions, it's essentially really difficult to say anything much concrete. Yeah, the complex structure and non-mean field criticality are real impediments. The full solution of the equilibrium dynamics might help for observables like the onset, right, which may be less sensitive to the structure of the liquid, but that remains to be seen. We'll see about the solution. And the last comment in passing, which may look obscure to some, but it'll be clearer tomorrow after those lectures, that maybe swap Monte Carlo will allow us to revisit some of this issue and obtain a sharper critical description. Right? That's the goal. Okay, let's get back to our table and see where we are. Okay, so we got rid of this. We know about the complex structure. I've talked about the upper critical dimension and how this may change the critical exponents. I've talked about nucleation, the random first order transition nucleation of the process of the type I've just described here. How in 3D it's most likely present, right? And it's present in every dimension. How big it is really hard to say. Like how significant it is, and one of the reasons behind this is because it may not be the only way in which activated processes or things kill the dynamical transition. What we're going to spend most of next lecture is looking at a different type of processes that kill the dynamical transition. But if it were the only one, we could probably say a lot. The same way that in a homogeneous nucleation in a crystal is a singular and pretty remarkable event. It's hard to identify precisely, but its consequences, and you can model it to some degree. Right? In a glass, if it were the only process, you might be able to say something more sharp, but it's really hard otherwise. Right? And this is completely absent in infinite dimension. There's two more categories here, hopping and facilitation, that I have not talked about yet. And to be able to talk about them in a coach, and one of the reasons I haven't talked about is because the microscopic theories we might have from those processes are really weak. Right? They're not the same sort of control that we have about the dynamical criticality or the nucleation in our FOT, which is connected to the point to set length that Ludo will talk about tomorrow as well, right? So it's not that we have complete theoretical control over them, but we have more than we have over processes like hopping. And no, but the same way you don't see any significant changes to the Ising model if you go above 4 dimensions. The critical exponents get a bit different, so presumably this is what you would see. But gamma is not a good critical exponent to look at because it changes with all dimensions anyways, and no one has looked at mu and no one has looked at the square root singularity. If you ask me in a few months, maybe I'll say there's something qualitatively different. But for now, no one has observed any such significant difference. Yeah. Oh, I thought you had a question as well. Okay. Yep. So if you go well above phi d, you will lower this barrier in all dimensions, right? But infinite dimension, it's still going to be infinite. Okay. So no, actually, I said it wrong. Take it back. The nucleation barrier is smallest at phi d. Every time you go beyond it, the barrier to surmount gets to be larger. Right, so if you go beyond phi d, you have less of a. So in a crystal nucleation, right, the further you go away from the transition, the bigger the difference in chemical potential that drives the reaction. But here it's different. The drive is the configurational entropy, and you know that if you go beyond phi d, this configurational entropy gets smaller and smaller. Right, so that drive actually shrinks if you go away from phi d. It is maximal at phi d, where the barrier gets to be really small. You can essentially just sail out of it, and you can make so it's the opposite in terms of going away from the transition and the driving force. So if you go to higher dimensions, what happens is that in all cases the barrier will get higher as you go away from phi d, and if you're at phi d at some point in infinite dimension, you will actually be arrested there fully. You won't be able to leave it. That's what I want to say. Okay, so no, not necessarily. It may or may not. Why not? Well, because for the same reason that in an Ising model you have a critical slowing down associated with approaching the critical point that has nothing to do with going from plus to minus magnetization. Right? There's a critical point here. There's a growing structural relaxation time that just comes from the fact that you have a dynamical transition. But you were never in the glass solution, right? You're not here. If you're above phi d, this is a smooth curve. If you go beyond phi d, then sure, that's the only process if you think this is the only process possible. What I will argue next class is that it's not the only process possible. Right? And actually, this is a very profound, it changes in a very profound way how we think about activated processes in glasses. So in spin glasses, this may be. In certain models, this may be the only process, but in structural glasses, it's not. To be able to, I'll mention this quickly in closing, and I'll describe it again next class. Because what we're going to do to be able to understand better the criticality and activation is that we're going to look at a model that Romain Mari and Jorge Kurchan first formulated about a decade ago. And their motivation for looking at this particular model, which I'll describe in a few minutes, was that you would expect this model to have, at the time, you would have expected this model to have a perfect critical point at the dynamical transition. This model should have no crystal nucleation, it's sort of mean field in nature, so it should have no corrections to the mean field critical exponent. It should have no RFOT nucleation. Right? So if you look at our table, right, it should have none of this. It has a trivial structure. It is not this. It doesn't have nucleation. And therefore, this looks like this should be the perfect model to study the dynamical criticality in this pseudo finite dimension. Right? Now, if I tell you what the model is, so this is a Hamiltonian. They're hard spheres with kinetic energy and with a hard sphere interaction. And the only thing that's different from the regular hard sphere is that I've added here this shift. Right? There's a vectorial shift. Each pair of particle has a random shift in their interaction. Right? And I choose this random shift anywhere between 0 and the box side in all the dimensions that I'm looking at. Right? So the interactions are hard spheres, but the impact of this shift, and actually in the way they first formulated the model, they considered here this the upper bound to be a tunable quantity. Right? So you can go, if you make this 0, you recover hard spheres. If you make it all the way to the box system side, and the shifts are fully delocalized. And so this is how you would look at 3 particles in a regular hard sphere system. So if 1 is close to 2 and 1 is close to 3, 2 is close to 3. But if you include random shifts, right, 1 can be close to 2 once shifted and close to 3 once shifted, but 2 and 3 have their own random shifts, and they could be really far from one another. Actually, typically, they are really far from one another. The result of which, right, if I look at what's close to 2, well, close to 2, there's 1, because it has a mirror shift, but 3 is really far. And the consequence of this is that all correlations of higher order than the 2-body correlations are trivial. Right? The truncation of the equation of state to the second virial coefficient is exact. Right? You don't have any complex structure. And one of the outcomes of this is because you can't define interfaces really anymore. Right? You can't separate the system in 2, so you can't have a nucleation process. So you can use a monodisperse system, and you can be sure that there won't be any drive to leave the minimum because you can't form that interface, right? Quite simply. Right? So it's really a wonderful model to look, or presumably look at the dynamical criticality. And this is how it was understood and how it was formulated in a certain way. And what we're going to do tomorrow is look in all the ways in which this premise was wrong and what it teaches us about relaxation in glasses. So, thank you for your attention. But we get to talk later, right? We get to respond to questions later.